Okay, so probably we can start. So, hello everyone. I'm Pavlo Gavrylenko, and I'm going to teach something about 2D CFT, starting from quite elementary things. So maybe first let me write my email where you can ask anything. And I will also ask you to write your emails at some moment. So here it is. So so what is CFT in general? It is some quantum field theory. So in our case, it will be two-dimensional quantum field theory. With conformal symmetry. CFT with conformal symmetry. Namely, it means that it is some machine which allows you to compute correlation functions of the operators like Z1, Z1 bar, and so on, all N of Z and Zn bar. So there are some complex numbers of these correlators, and the interesting operators, of course, not all of them are of this form, but the interesting operator such that everything else can be reduced to them have a property that they behave like differential forms of some probably fractional weights, like dz 1 to delta 1, dz 1 bar to delta 1 bar are kind of invariant. So, and application this CFT is interesting as itself, but it can also have applications to many different topics in theoretical physics and mathematics. So one thing which we will investigate in detail in some simple examples like free fields or free field or Ising model. Its application to 2D statistical systems. So, namely, the situation there is the following: that there is a lot of different theories. For example, we can take ordinary scalar field with some potential v of phi. So consider, for example, the action of this kind. S of phi equals to integral of d mu phi, d mu phi plus v of phi d to x. And say that this is this v of phi is, for example, polynomial. If we restrict to polynomial potentials of some order, it can be some finite dimensional space. In general, it will be infinite dimensional. But the point about this space is that if we try to look at such theories from Renorm Renorm group point of view, it turns out that this is the infinite dimensional space of how to say of marginal operators, because in 2 dimensions dimension of phi is 0. So all these phi ends are marginal. And it turns out that in this case we have I don't know how to write it, but we kind of have a modular space of such theories, and we have some Renorm group flow on this space, like. And there are some fixed points of this Renorm group flow. So it's of course somewhat a dimensional picture, but if you project it somehow, it can have this form. So there is a lot of fixed points of this Renorm group flow, and the infinite number of these points. In this case, I would say all of them can be classified using the general theory coming from CFT. So all these fixed points which are at the same time second order phase transitions. Because if you are in the fixed point of normalization group, it means that, for example, two-point correlator, which in general decay exponentially, is of order e to the x minus y over some psi correlation length over some power of some 2 delta probably. So at this fixed points, this psi goes to infinity, which is correlation length. And this theory acquires scale invariance, and in 2D, in most of the situations, scale invariance means conformal invariance. So all these fixed points of normalization group or these phase transitions correspond to some CFTs. And actually, in this particular theory, for this particular theory, this fixed points can be all classified, and they correspond to minimal models like M. So for this theory, they are M P plus 1. And we will see. We will look at one example of such a theory, which is the Eisen model. So another application of CFT is to string theory, which I think we will not consider or will touch just a little bit. So it is related because Polyakhov's action of a string and also its analog for a superstring has the form of sum of several such free fields, at least if we work in the flat space-time. It looks like dx mu, d bar x mu, d2 z. So d mu d bar is up to some factor the same as dA x mu, dA x mu. So another relation of so another application of CFT, which actually, in some sense, is not an application of CFT, but application of the gauge theory to CFT. It's the AGT correspondence. Which say that conformal blocks of 2D CFT are equal to instant on partition functions of for D n equals to series gauge theories. And it is useful in the opposite direction, because the expressions for conformal blocks are usually not very good if you use some naive basis. But these functions are very nice, factorized and so on, so they give efficient formulas for conformal blocks. And maybe, so probably we'll touch it a little bit, but mostly starting from the other application of CFT. And this application is called isomodromic deformations. Or Penrose CFT. And this was discovered by Gavrylenko and Lisovy. So can be called GIL. And AGT is for Dagger and Chikala. So, and the main example of this application, the statement that the following autonomous system, let me maybe write it explicitly, like dAI over dzj equals to ii aj over zi minus zj. This is an autonomous system. Is solved by CFT. And maybe the simplest example of the system which can be written explicitly and can be understood is an autonomous Colliger-Moser system. Like this equation and also the following equation: 2 pi I d tau squared of q of tau equals to m squared Weierstrass function of q of tau of 2q of tau like so it's time dependent. It's it's classical particle which moves in a time dependent potential. So a solution of such an autonomous equation, which is non-integrable in the Liouville sense, can be written in terms of conformal blocks. In this case, on autonomous. So it's some kind. It's somehow not completely CFT. It's only a holomorphic part of it, but yes. Mm. Ah, yeah. Yes. So, and also closely related problem is a problem about eigenvalues of a quantum operator of the same kind. So spectral problems like for the system, but it's quantum version. Minus dx squared plus m times m plus 1 Weierstrass of x tau. So it's it's called llama potential. So there's material potential. There are some modifications of this llama potential. So these problems can also be solved using some objects coming from CFT. So if you know, if you heard about central charge, so this is more or less C equals 1, and this is C equals infinity, but it is also related to the to C equals 1. Okay, so this is what I want to tell at the end. Well, there are, of course, other applications, but I will mostly tell this. And so it was some introduction, and then I'm going to start from some elementary definitions from classical field theory and so on. So are there any questions about the introduction? Okay, so probably let me go to the whiteboard and start from some definitions. So so when I told that CFT is some machine which can compute the correlators for you, I meant that not any CFT has Lagrangian description, or at least it is known not for any CFT. What can it mean in practice? So everyone can think that it means that it is something ununderstandable or very complicated, like non-Lagrangian theory, what can it be, and so on. But in practice, it usually means that we cannot write precise Lagrangian for this given CFT, but we can consider some other theory. For example, this free field theory or something like the Eisen model, and consider the limit to the point of second order phase transition, and this effective theory around it will be conformal. So it means that Lagrangian theories can be understood as the limits of some Lagrangian theories, and in this sense they're nice. Another way to think about this is that we can really forget about Lagrangian formulation and say that there is some algebraic structure which can compute the correlators, and it can also be understood quite well. But nevertheless, I want to start from the assumption that our CFT has some Lagrangian description. And I want to say that correlators can actually be computed as some maybe let me write in this way: ln of xn can be computed as some path integrals, like integrals over all possible configurations of a field e to minus s of phi. It is a functional of phi, and oh, sorry, this is the definition. And now mm, I need to say what is the meaning for all these objects. So when we write d phi of x, it means infinite dimensional integral. And maybe the easiest way to understand this is to say that it's an integral over uh, uh, no, how to say it? So it's so this measure is the product of differentials of the value of our field in all possible points of a real plane. So this is an infinite dimensional integral, and for practical reasons we can somehow discretize it and make finite dimensional. For example, consider lattice theories and then take limit when lattice spacing goes to zero and number of points goes to zero. So these fields O O of x can be for example, it can be our field computed at this point x. It can be its derivative, d mu phi of x. It can be some, for example, phi of x squared, which should be somehow nicely defined. It can be, and it is one of the main examples, it can be exponential of phi of x, also somehow well defined. And what is the action S of phi? It is the action of classical field theory. It is given by two-dimensional integral d2x of some function depending on the field phi and its first derivative. In principle, we could add higher derivatives, but our nature works this way that usually all theories have only first derivatives in the Lagrangian. So for example, it can be the integral of d to x d mu phi d mu phi. It is the first. It is the simplest example of conformal field theory. So, are there any questions about the definitions? Uh, uh, so, in some sense, it's an observational fact, but there are probably some other reasons, like um, if you have higher derivatives, then theory it can be non-unitary, but maybe depending on the point of view, the main reason is that if we take a normalization group flow and try to go to some fixed point, all higher derivatives will usually be irrelevant and they will die. Because in principle, we can take the lattice theory, which is perfect, which is unitary, and then shift operators which will be there. For example, if we have something like phi Laplacian of phi of x, sum of x, it will transform to cosine of 2 pi kx plus cosine of 2 pi ky minus 2 some phi k phi minus k. So we can say that there is a infinite number of so k squared is first is second derivative which can be distributed between phi and phi, and all higher terms are higher derivatives. So in principle, we can construct theories with an infinite number of higher derivatives, which will basically mean this lattice theories. But we don't want to. And if we are just one or two higher derivatives, as far as I know, they lead to some problems with unitarity in many cases. So, but we can think we just restrict to this case. So, are there other questions? So, okay. So. Let me now say a few words about this classical theory and what happens if we ask for conformal thing, for conformal or for some other symmetry. So let us call it symmetry then. In classical field theory. But I'll better specify that they are continuous symmetries. So suppose that our action S of phi is invariant under some infinitesimal transformation, namely, sorry, should be written on the left-hand side. So suppose that if we take our field configuration, which we are going to put into this functional, and perform infinitesimal transformation, like phi plus epsilon, some operator acting on phi, so if it is invariant under the infinitesimal transformation, it means that it should be the same action up to the epsilon squared term. And epsilon is just some parameter, some real parameter. It means it's called infinitesimal symmetry. Also, just a definition. For example, if you look at this action, which is a massless scalar field, so if you look at the section, we can try to write a list of symmetries of it. And let us maybe try to write on this list. So, yeah, examples for this action. So which continuous symmetries of this action do you see? Like looking at this definition. Well, in which direction? Because there is kind of a target space translation and a worldsheet translation. So which precise transformation do you mean? Like what is G in X, right? So it means that f of x maps to phi of x maps to phi of x plus epsilon, right? But what does it mean in these terms? Like, what should we substitute as the infinitesimal, the operator of infinitesimal transformation of phi? Yeah, thanks. So we can write that maybe let us say that it is translation by some vector A, and it means that g hat of phi equals to a mu d mu phi. Right. So and who knows other examples? Yes. So. Hmm? Hmm? Okay. Mm-hmm. So there is transformation phi phi goes to phi plus c, which means that g phi in this infinitesimal version is just 1. So that's constant. So if you want to perform a translation, it means that we need to add some epsilon omega x, some transformation, some antisymmetric matrix, which is 0, 1, minus 1, 0. And it means that g phi equals to what? X dy phi minus x dy minus y dx phi, right? The vector field which rotates on this phi. So all these examples work in arbitrary dimension. And because theories are usually rotationally invariant, translation invariant, and if they are massless, they allow such kind of translation. But what is specific about d equals 2 for the scalar field? So we see there are two derivatives here, and there are two dx's here. So, yes. So if we consider phi of lambda x, phi goes to phi of lambda x. It is still invariance of this action because these derivatives cancel with these differentials and mean that we will get the same action. So in this case, g of phi equals to x x dx plus y dy phi. And actually, there are more symmetries, but let us stop at this point and go back to the general theory. So I'm basically going to prove Noether theorem. In this case, I want to show how this action I want to show how to get integrals of motion from such continuous symmetries, and what is the practical way to get them. So, by the way, it seems that ventilation switched off again. Yes, so we have this action with the infinitesimal symmetry, but we see that it should be invariant under such transformation. But there is also another situation where we need to consider the variation of action. And this is when we want to find solutions of the equations of motion. So equations of motion in a classical field theory are obtained and are equivalent to the list action principle. Namely, it says that so maybe let me write phi satisfies equations of motion. If and only if for any variation delta phi, action of phi plus epsilon delta phi equals s of phi plus O of epsilon squared. So it is equivalent to say that delta S equals to 0. This, and you see, if you look at these two statements, they look very similar. And so let us try to combine them somehow. Namely, let us try to consider phi which satisfies the equations of motion. And consider the following variation of the action. Consider S of phi plus epsilon of x. So we make this parameter of the transformation coordinate dependent. Maybe let us do it. Sorry, let us do it. No, it's fine. So if phi satisfies the equations of motion, then it equals to S of phi plus O of epsilon squared for phi any epsilon. So we have just chosen such a specific variation of phi, which is not generic, but if it is zero for generic, it should be zero for this one. And now, so it's for this case. And now consider the same expression for generic phi. So we know the structure of the action. It's an integral of Lagrangian of phi and its derivative. So if you have such an expression, you can always do integration by parts, and the result of this integration by parts will be something like this. It will be integral of d2x epsilon of x times some function of let us just say that it is function of phi d phi x, probably can enter explicitly, so on. But what we know about this integral, that if we substitute epsilon equals to constant and phi arbitrary, it will vanish. So so what can we say now? So it's some differential polynomial of phi. Probably it's x dependent, but if its integral over the whole space vanishes, it means that it should equal to some combination of derivatives of some functions. So we can say that this probably I should go to the other block, or maybe to this one. So let us say that we are considering here two situations. One is this one, another is this one. So from two we get that s of phi plus epsilon of x g hat phi equals to the integral over 2x, and let us write it this way: epsilon of x d mu some g mu of x. So non-trivial statement is that there g mu of phi d phi dx there exists such g mu. It follows from the symmetry, because it should vanish for constant epsilon. Oh, sorry, I forgot to write the main part. Sorry, plus s of phi plus O of epsilon squared. Is it fine? No. And of course, you see that this g mu is not unique, because we can add some derivative, for example, of an antisymmetric tensor. So there can be other choices. So, and from one we get that this difference that s of phi plus epsilon of x g phi equals to s phi if phi satisfies equations of motion. So combining these two statements, we get that. This works for arbitrary epsilon. This formula holds for arbitrary epsilon, for any epsilon of x. So if it holds for any epsilon of x, it means that this term just identically vanishes. So if equations of motions are satisfied, then g mu equals to 0. This approach with kind of broken infinitesimal transformation with coordinate dependent infinitesimal transformation gives a practical way to compute these integrals of motion in some field theories. Because the only thing we need to do is to reduce everything to the terms which have maybe it's even easier to integrate it by parts and say that we should have terms which contain only derivatives of epsilon and not epsilon itself. So if we are able to check that the action is invariant under infinitesimal transformation, then we are able to do also this. Because if we see that this variation is zero, we should understand why it is zero, like why it is a total derivative. So and now let us apply this approach for this theory and find a conserved charge which corresponds to this target space translation. Maybe it's better to put here 1/2. Or maybe from the very beginning some 1/2 squared. So so S of phi plus epsilon equals to 1 over equals to S of phi plus 1 over d squared integral of d mu epsilon d mu phi d2x. And we see that it means automatically that our conserved current is d mu phi, 1 over d squared d mu phi. So yeah, is it fine? So so what else can we see? Let us also try to find energy momentum tensor of this theory. So, namely, if you have translations in the worksheet, we know that the same should hold, like S of phi plus let me write it like epsilon nu d nu phi is equal to S of phi plus a integral of T mu nu. And better write it this way. D mu epsilon nu plus d nu epsilon nu. So I actually forgot what is the correct sign here. Probably 1/2. Probably also with a minus sign, but it doesn't matter of definition. So let us try to compute it maybe in the d-dimensional case to see the difference between 2D and arbitrary dimension for the same theory. So we have integral over dx 1 over 2g squared d mu phi. So I will only write this variation term. So this 1 over g squared d mu phi and the d mu of this variation of phi. Epsilon, use some other letter, d rho of epsilon epsilon it was fine. D mu phi d mu epsilon mu d d mu phi. So if we integrate, if we compute this derivative, it will be 1 over g squared integral d mu phi d nu epsilon mu. This is the term we like, d mu phi plus another term that we don't like, since it's proportional to epsilon, and it is integral of epsilon mu d mu phi. It's sorry, so it is mu and it is nu. Sorry, let me check. Oh, it is d. So now it's fine, right? Thanks. So, and this term is d mu phi. Now it's d nu phi d nu d mu phi. So it can be written as total derivative of 1/2 times total derivative of d nu phi. So it is mm, mm, 1 over d squared mm, integral of mm, d nu phi d mu phi d nu epsilon mu uh, plus and let me already integrate this by parts. So do two procedures at the same time. Write it as a total derivative and integrate by parts. So it is minus 1 over 2g squared integral of d mu epsilon mu d d nu phi d nu phi. So is it fine? Mm. And mm, so we see that this term contains derivatives of epsilon as expected, and this term also contains derivatives of epsilon. And if we now compare this with this definition of the variation of action by coordinate dependent transformation, which is actually the first order of some of the flow of vector field epsilon. Epsilon. So if you compare this transformation, this one with this one, what will be the formula for T mu nu? So T mu nu, maybe this one, equals to, who can tell this? So if you want to compare this result of the transformation with this term, so which T mu nu should be written so that these two formulas match. So the difference is that here I symmetrize these derivatives of epsilon, and here just one derivative, but this term is symmetric. So uh, yeah, so d mu phi d nu phi with coefficient 1 over g squared, right? this one, because if we combine it with this expression times 1/2, it will give precisely the same term two times. It will cancel 1/2. And what about this term? What, so, so it is 1 over 2g squared. Uh, hmm? Yes, some yes, the row of uh, phi d rho phi, right? Mm. So it's the formula for the energy momentum tensor. And now I can also raise this. So it was at this moment it was a kind of definition of this energy momentum tensor. We could just take this translations and say that corresponding neutral current is T mu nu. Oh, but and now let us see what are the properties of this T mu nu. Um, so maybe let us just compute a trace, namely a trace of T mu nu, which is like trace of T equals to T mu nu. It is 1 over g squared d mu phi d mu phi minus uh, let us call dimension of our space d minus d over 2 d squared d mu phi d mu phi. So we see that it is proportional to 1 minus d over 2 times something. And when d equals to 2, it vanishes. Which can be understood also in some other way. So, namely, we wanted to spoil this transformation somehow by making this vector coordinate dependent. And we used it to obtain this formula for the energy momentum tensor. But if you look at these transformations very well, there are some transformations which are actually symmetries of original theory. And we can try to use one of these transformations instead of arbitrary epsilon. So let us consider the general situation. Let us use a scaling transformation. namely, say that epsilon mu is just x mu. And in this case, our action will transform as so. So if we do this, and then d mu epsilon nu will equal to g mu nu, yeah, just to g mu nu. So S of phi plus epsilon x mu d mu phi will equal to the integral to S of phi plus the integral of d mu mu actually, so let me think. We can say that we want this epsilon be coordinate dependent as well. No, sorry. So yeah, if we do this way, then we get d mu epsilon of x d 2x plus the term where we differentiate epsilon. Sorry. No, sorry. Actually, now I'm going to prove, well, I'm going to prove statement which is wrong, because scaling transformation, because the tracelessness of T mu nu does not follow from scaling invariance. There are some examples of theories which are scale invariant, but are not conformal invariant. For example, two-dimensional elasticity theory is an example of such a theory. So we can say in the opposite, like the action is S of u mu is d mu u nu plus d mu u nu squared, probably plus some coefficient d mu u nu squared. So this theory is a scale d to x, a scale invariant and it will have a trace of t mu which does not vanish identically. So we can only say that if a trace of t vanishes, then this scaling transformation will be trivial. But actually it will give much more than this. Because let us so let us try to consider some theory which has zero trace of energy momentum tensor. We start from so we checked that it is a scale invariant, but let us let us see what other invariants that this theory have. And to study this, it is very convenient to switch to complex coordinates. Say that there is some coordinate z which is equal to x1 plus I x2, and there is z bar which is equal to x1 minus I x2. And if we write a matrix for this complex coordinates, which was initially x1 dx1 squared plus dx2 squared, will now equal to let us write it like 1/2 dz dz bar squared. Oh, sorry, dz bar plus 1/2 dz bar dz. So it is symmetric tensor. So maybe it's better to write like dx1 tensor dx1 plus dx2 tensor dx2 equals to 1/2 dz tensor dz bar plus 1/2 dz bar tensor dz. So this is what happens with the matrix. So we get some 1/2s here. And there was also the volume form, which appeared in the action. Uh, so our original volume form was uh, but we'll not use it actually. It's better just to see once what happens with it. So original volume form was dx1 edge dx2, and after this transformation, it turns into uh, mm, so mm, probably the 1/2 uh, I over 2 d the 1 mm, no, there should definitely be uh, some I, because if you take a dz wedge dz bar, we have dx1 wedge dx2 with coefficient minus I, and the same term from this from these two. So it's also sorry, yeah, dz wedge dz bar. So in this complex coordinates, uh, this epsilon tensor is like 0 I over 2 minus I over 2, and uh, a metric is 1/2 1/2 0. Mm. And sometimes we can get some combinations like g plus minus epsilon plus minus I epsilon, and these are kind of projectors, some objects with uh, objects of rank 1. So they can appear in some self-duality equations in two-dimensional theories. So it's not just coincidence that epsilon tensor and matrix in this complex coordinates look almost the same. One is symmetric matrix, another is anti-symmetric. But what for I'm writing this is to say that and now tracelessness condition of the energy momentum tensor means that its ZZ bar component should equal to 0. So let me maybe erase something, probably this definition of the parameters. So I forgot to say that in this condition, which which we want to consider is defining a property of CFT. This is Okay, so now we want this condition t mu equals to 0. It means that g mu nu t mu nu equals to 0, which is equivalent to t z bar equal to t z bar z equal to the same with the upper indices equal to 0. And the only non-zero components of t are t z z and t z bar z bar. And if you want to switch from upper indices from lower indices to upper indices, there are some stupid factors of 4 probably, or 1/4, depending on the direction, which come from this 1/2 in the metric. So this is a metric with lower indices, and if we want to switch from this to upper indices, we should invert it, and we get something like t z z equals to 4 t z bar z bar. So in this relation between different components of energy momentum tensor, the same for t z bar z bar. So now let us try to look at this transformation law for the action under the assumption that energy momentum tensor is traceless. So we will have only two terms. So S of phi plus epsilon g hat phi equals to the integral of like 1/2 maybe it's better to use upper indices. T z z no, so maybe integrated by parts. No, first write it as is. So it is a t z z d z epsilon z plus t z bar d z bar epsilon z bar. But and probably without without 1/2. we can also use this metric to rewrite to raise indices of this epsilons because we see that the components of the vector field which shifts our coordinate are upper coordinates. So we should write something like epsilon z equals to 1/2 of epsilon z bar, and use it here. So it equals to 1/2 integral of t z z dz epsilon z bar plus t z bar dz bar epsilon z. So now look at these formulas. We see that our vector field has two components, epsilon z and epsilon z bar, and derivatives which appear in the sum are only z and z bar derivative. So if we take epsilon z bar to be anti-analytic function, and epsilon z analytic function, which means that corresponding derivatives vanish. Yeah. Epsilon. So it means that this is epsilon z bar of z bar, and this is epsilon z of z. So it will mean that our action so in this case I have to write here epsilon nu d nu phi. In this case we will see that this s of phi plus epsilon nu d nu phi will be equal to s of phi plus O of epsilon squared. So it means that demanding zero trace of energy momentum tensor, we get something more. We get an infinite algebra of symmetries, and the symmetries are translations by such vector fields, which are homomorphic. No, probably it can be called somehow. So to say it in some simple way, we can say that this vector fields come from the coordinate transformation. Z goes to some function of z, and this f is analytic function. The only problem with such symmetries is that if you work on a complex sphere, so if you want to consider our theory on some compact manifold, for example, on a sphere, then there is not so many analytic functions which will be bijections. For example, if you want to map CP1 to CP1, Uh, uh, and if you also want this transformation to be invertible, the only option we have is to write some function with single pole and single zero, because it should be one-to-one, so zero should have one preimage, and infinity should have one preimage. So this f of z is a z plus b over c z plus d. So it is mm, a three-parametric family of functions. But this is if we want to think about global symmetries. Locally, we have an infinite number of such symmetries, and if we so it's some local statement about the transformation of density of the action of this theory. So even if we cannot present global transformations, it's still some it's still something very important. And if you want some interpretation if you want some global interpretation, then we should think about theory with a boundary. So CP1 does not have boundary, but if we introduce some theory which lives in domain D with some trivial boundary, then such transformation Z to f of z will map this theory to some other domain f of d with some other boundary f of boundary of d. And the statement will be that, for example, equations of motion in this theory with different boundary can be obtained from equations of motion in this theory before the transformation. And partition functions of this theories will be written in the same way. Like the density of the action will be the same. But if you want but if you want some actual symmetry which maps theory to itself, we should restrict to the transformations which preserve boundary, and it's even smaller subset of these global transformations. There are transformations which preserve equator of the sphere or some other circle. Oh, okay, so at the moment we see that if we start from a theory with traceless energy momentum tensor, we will get some theory which has extra symmetries. It has this conformal symmetry. So maybe I can say that this is conformal symmetry. And so it was consideration for the situation when all fields are arbitrary and this vector epsilon satisfies this homomorphic conditions. And now let us switch our setting to this maybe first option where epsilon is again arbitrary, but fields satisfy equations of motion. Maybe so which blackboard to use? Maybe the next one. So now epsilon z bar arbitrary. So and maybe we can again rewrite this action in terms of t with lower indices. So s of phi plus epsilon nu d nu phi equals to 2 t. So we want to integrate all this by parts, and it will be epsilon z bar d z t z bar plus epsilon z d z bar t z z. So like this. And we know that if plus s of phi, we know that equations of motion are satisfied, then we know that these two terms dz t z bar equals to 0, and d z bar t z z also equals to 0. So this is the typical situation in conformal field theory, that if we have some conservation law in the usual field theory, then we have just d mu equals to 0, which is like d z g z dz g z bar plus d z bar g z equals to 0. So this is what happens in the ordinary field theory if we try to rewrite it in complex coordinates. But if we theory, then usually this homomorphic conservation laws mean that dz g z bar is 0 and dz bar g z is also 0. So this is what usually happens in CFT. And actually, in this case, in general, it probably there is no simple explanation why it happens. But in this particular case, it is easy to understand that we could, in principle, get this homomorphic and anti-homomorphic conditions just from conservation law and from tracelessness of TZZ, because we have conservation law that says that dz t z bar plus d z bar t z bar equals to 0, like we sum over on this two indices, and since it is identically traceless, we are left only with one condition, which is this anti-homomorphicity condition for T z bar, and the same for the other component. So we see that all this leads to a very rich structure, because there is a infinite dimensional algebra of conformal transformations. We have some homomorphic and anti-homomorphic functions as integrals of motion. So it means that this theory should be much more solvable than the arbitrary quantum field theory. And so maybe that's all I wanted to say today. Are there any questions? Or, mm-hmm. We know that transformation of the action has this form. In principle, we had another third term which contained T z bar, but we told that T is traceless already. We want to consider conformal field theory, so it's absent. So now we have two terms with formally independent epsilon z bar and epsilon z. So in principle, so it's always in CFT that we have z components and z bar components, and in principle, if it is an actual vector field, we should say that they are conjugate to each other. But we can choose different bases in the vector fields and always say that these components are independent or on a complex number. So we have two independent epsilon z bar and epsilon z here. So it means that these components should both be 0. So is it fine? So it is in this particular case, and in the general case, we should see like if we want some other symmetry, then this translation symmetry, which gives rise to energy momentum tensor, we should just check that transformation properties of the action contain uh, so So in the general case, we should check that action is invariant under homomorphic and anti-homomorphic transformations. For example, in this case, probably we'll discuss it next time. Where is So in the case of this 2D field, another homomorphic symmetry is a coordinate-dependent shift of the vector of the shift of the field phi. So we can add a homomorphic or anti-homomorphic function to it, and the result of this conserving current d phi will also satisfy two such conditions. Actually, actually it's obvious because d bar phi is 0. It's so other questions. Okay, then thanks for your attention. And probably I will ask you to write your emails in case I need to tell you something or send something. So can you please write them, like names and emails on this side of this sheet? And we are asking the other people the next time. Uh, Actually, it's a question to you. Like, what do you think? Should I go faster, or is it fine? Mhm. Ah. Hmm. Okay. So. Hmm? So and maybe and can you tell me your names? I do not remember from the for the first time, but I'll ask you later. Like, what are your names and what are you doing? Like, who is of which year? Can, so, who in the first? Uh, so, what is your name and what are you doing in science and what are your interests? Okay. Mm. Mm-hmm. Mm-hmm. Ah. Mm-hmm. So. Mm-hmm. Ah. See. Mm-hmm. Yeah. So. Uh, mm, and you also, right? Mm. Ah. Mm-hmm. Mm-hmm. Okay. So probably. Uh, mm, it means that I can go faster, right? So, but I think um, I should anyway derive a conformal world identities, right? Or does anyone know this? Ah. Okay, so maybe this time I will end with this classical considerations and start deriving conformal word identities to compute some correlators of the free field. So, but if it becomes too fast, just tell me, or if it is too slow. So, welcome. Well, next time is on Thursday in the same room. Yeah, that's
Okay, so I didn't know that just scaling variance. Okay, scaling variance alone, so the tracelessness of the stress energy tensor implies full conformal invariance in 2 dimensions.
yes, tracelessness does imply. But,
Classically, no. Scaling variance, I mean, like when you have. Okay, I know that Poincaré plus scaling variance, that is conformal invariance. That is okay. Yeah, but the point is
no.
you have Lorentz invariance. Together with scaling variance, you get conformal invariance.
No, and there is this example. It was told by Slovarchkov. This is a two-dimensional elasticity theory, which is not conformally invariant.
But this is not Lorentz invariant. That's not Poincaré invariant.
No, Poincare in this case is just rotations and translations. It's 2D.
As far as I know, there is a theorem by Pavlo which states that a theory which is Lorentz scaling variance is conformal invariant. Classical. But I also know that classically scaling variance alone implies. No, I think that is conformal. No, I'm sure. That is only for scaling variance. I think that just the scaling variance implies this. But
what to do with this example? Like, what is wrong with it?
Because that is not Lorentz invariant.
No, why it's not?
Because you have an explicit coordinate dependence.
No, it's kappa. It's coordinate.
Sorry.
Yeah.
I thought it was no. I thought it was an explicit.
Maybe some lambda. So there are some coefficients of elasticity tensor, and we can write this action. Maybe this first term is enough.
Maybe because it's not like if I consider it as a theory.
So the problem is that we should,
I'm talking classical, yeah, not
no, but even classically.
When you put these theories on manifolds and you compute the trace of the energy tensor, you have by the anomaly, okay? Which is the fact that the stress energy tensor is not it's a quantum effect, whatever. But this is the breaking of conformal invariance, not of scale invariance. That's what I'm saying. As far as I know, that's why that's why I don't know. But isn't scaling variance a subgroup of conformal invariance?
Yes.
Yeah. That's why you break it as well at the quantum level. Yes, but no. I mean, like the conformal proof is you have Poincare plus dilations plus special conformal transformations. So if you have Weyl anomaly, I guess you also have problem with dilations, right? Like the point is the fact is what you're saying is true on Rn, but you are on a manifold. On a manifold, like you don't have the transformation yourself. Okay, yeah, sure. Yeah. Sorry, but I knew this theorem of Pavlo. So why this doesn't apply to that?
I don't know this theorem, but isn't he asking for something more like that the theory is some kind of unitary or?
So you're saying that there are many time derivatives in this action, or space derivative, whatever?
I don't know. So I don't try to study what are the problems of this theory, like what is wrong with this.
No, because like the reason why you can use CFT for describing second order first transition is indeed because of this theorem. Because you would have just scaling variance, but you can actually promote to conformal invariance. That's at least the fairy tale I was told. So that's theory. That's a classical theory. It's not a quantum theory. No? Meaning that that doesn't work quantum mechanics. That is just a classical example. Okay. But I mean, later we can have just like two derivatives in any case. Yes, that's also the problem that I'm thinking about, because to me that's a legit Lorentz invariant action with at most two and derivatives, so shouldn't lie.
So here the problem is so how to formulate this. The problem is how to put z and z bar, and how to say that someone is holomorphic and someone is anti-holomorphic. Like, but I think I'm not sure. Probably I need to Google for this theorem and check the assumptions. But as far as I remember, it is a small logical jump that scale invariance should also imply conformal invariance. In a sense, it is not something automatic. So, and if we try to think about this example, maybe just on this one. So the problem is that if you study the scale invariance of this theory, it is very stupid. U is of dimension 0, and so these two derivatives cancel with what is going from measure. But if we think about, for example, so rotations are also fine. This is rotationally invariant. But if you want to assign some conformal dimension to this U, how should we do this? And there is, for example, in conformal coordinates UZ and UZ bar. They have 0 conformal dimension. They have 1 and -1 dimension with respect to the rotation. So it looks like just a contradiction. So is it clear what I mean? So the scale.
I mean, like the kinetic energy operator is let's say is not invertible in some sense. That's what you're trying to say. That you cannot isolate one single well-defined kinetic energy operator with respect to the compute the scaling dimension of U.
No, probably I don't know if it can be interpreted this way. I'm just saying that if we want to make this theory conformal, we should assign some conformal weights to U. And there is a contradiction because scale transformation is U nu goes to lambda u nu uh, rotation is u z goes to e to the phi u z u z bar goes to e to the minus I phi u z bar. From the point of sorry of lambda z, so it is scalar and e to I phi z to the phi z. So it is a kind of scalar with respect to the scaling transformation and uh, vector with respect to rotations. So, but actually, no, I don't know. If we think about this more, it could in principle mean that it has dimension 1/2 minus 1/2. And another one is minus 1/2 1/2. Hmm? Oh, what?
The difference of the conformal dimension.
Yeah, yes. Now.
Okay, but it's not scaling the part.
So its scaling dimension is 0 and spin is 1. So actually, I don't know. Maybe if you try to do this way, um, I actually need to check. Maybe it is conformally invariant, and it's just not a counterexample. But it was given as a counterexample, and naively I crafted this from this argument that it cannot be at the same time vector and something different from vector. But mm. Then probably one would need to check that everything is fine with these terms, like the number of uh, z's and z bars is correct. Well, probably I'll check it at home and check if it's possible to write as this energy momentum tensor. So,
Another way of solving this is like to show that if there is a way to make it invariant under unscaling of dimension. Like, because this can be made like invariant under diffeomorphisms just by changing derivatives with covariant derivatives. But you can also, like, if you're able to show that there is actually a way to make U transformer in order to cancel the Weil factor on the metric, then the theory is conformally invariant.
So if you want to introduce here the matrix, metric, and we should mm, mm, so it will involve a metric squared here, and here we will have a square root of a metric.
What this just yes, metric squared. Yes, I mean this is okay.
So, like, it is a metric with upper indices, so it is inverse. And here we will have a square root of determinant of metrics, a metric with lower indices. So this one will definitely be wrong because it will not be scale invariant. We will need to add another square root of g.
But in principle, I can also allow transformation of this.
Yes.
If they like behave as constant bosons of a broken wave transformation, like in UV theory. In principle, we should allow also this. But
Yes.
probably this appears with a derivative. I wouldn't be able to cancel the factor here.
So, but I will definitely try to assign these conformal weights and check if it is possible to get a traceless energy momentum tensor with such conformal weights. If no, probably, well, probably it will still mean nothing because.
Thank you.
You're welcome. By the way, what is your name?
My name is Leonardo.
Could you say it again?
Leonardo.
Yes.
I study quantitative problems.
Ah.
Like in the moment, I'm focusing on effective electronics, satisfaction for focus systems.
Ah. I see. Mhm. So, welcome. See you. So I need to stop the recording.